Hello everyone. Okay, so um, I will show how you could solve the inverse kinematic problem, right? With a lot of links, basically the bonus part from transformation. And again, I'm not going to do that on JavaScript. I will still using 3 to the max. It's easier for me to explain because everything is like literally there in 3D and I can explain. And also because I will never give you the solution like the entire thing, right? Because you need to write your own code. And even if you didn't finish this, I think some of the students were interested in actually computing this, and it is important, right? I mean, this type of like challenging projects are very good projects for you to like show when you finish your degree and look for employment, or maybe to create your own company, whatever, right? And yeah, so I hope you are kind of enjoying this type of challenging projects, and yeah, I hope you like the video. Okay, so I have an end effector here already, and I animated the end effector to basically follow this path, right? With no other purpose of just having an end effector like moving on, kind of like, yeah, moving in 3D in a kind of interesting way, right? I mean, obviously this is not exactly necessarily related with the solution itself, right? In the end, the inverse kinematic solution will need to be exactly the same, right? Or it needs to work. That doesn't matter the movement that the end effector is doing. Okay, so then I will, give me a second. I will create some like boxes. So these will be L01 and I don't know, 15 maybe, 1.2, 1, and maybe like this. Yeah, again, it doesn't matter too much right now. I'm like in code we will get this information from the object directly, right? The height of this object and everything. I need to, yeah, basically create more links. So I will just copy this guy twice. Yeah, so at least for now we can just experiment with this system, right? The kinematic chain with 3 links. After this, if the code is working perfectly, we can just expand it to whatever amount of links we want. But yeah, this is enough. So this is L1, L2, and L3. And let me open this thing right here. Okay, so the first thing we need to do is, okay, so the first thing we need to do is create a kinematic chain variable, which is basically an array with these objects right here, right? L1, L2, and L3. Yeah, I will copy. I will not necessarily like show the entire like writing of all lines of code, because that will just make the video longer. So I will probably, like, every time I'm maybe writing something, I will pause and then I will explain, right? Okay, then I need to copy from other scripts. I need to copy my function for circle intersection. So this is my function, right? I mean, there's no surprising here. This is already explained on one of the videos. This is my triangle theorem to compute the intersection between circles. But again, remember, this is just an algorithm to compute the intersection between 2 circles. There are other ways to compute it. You can go online and, yeah, you can use trigonometry or whatever you want, right? I will collapse this function. I will also get my lookat transformation function, which basically, remember, gets the position of the object, the position of the target, and it gets an up vector, right? And with those vectors, or with those positions and vectors, it will basically compute the new matrix, right? With a rotation part and also translation part, and that is exactly the transformation that it will assign for every for every object, right? So this is exactly the same, and this is already here. It's already solved the problem that we had on the previous video. Remember, I made a mistake of switching two variables in a cross product in the first video of inverse kinematic. Well, this is the correct version, right? I'm also explaining this on the extra video from the midterm extra. So if you're seeing this video, the other video is also already in the on the web page, and I explain why the problem was there and what is basically the solution, right? So this is the correct version of this. Okay, so what we want, we probably need a function, maybe something like solve IK, something like that, from which I could maybe send the kinematic chain, right? Maybe like send the array of links, and that could be a recursive. We can make it recursive, right? So the way we need to solve this problem, remember, is that we need to use these virtual links, right? So the easiest way to solve the inverse kinematic problem is when you only have two links, right? So if you have more than two links, the trick is that we will assume that we will solve the kinematic problem for the last link, and for a fictitious or virtual link, right? Not this link and this link, but maybe literally a fictitious link. Let me show you an image. So this is what I mean, right? So if I have a kinematic chain like this one, right? This one has 4 links, L1, L2, and L3, and L4. My first computation will be J1, and J1 is basically an inverse kinematic solution for 2 links. One is the last link of my kinematic chain, which is L4, and a virtual link, which is this one, right? Whose length it will be determined by my algorithm, right? So now, once I basically solve that inverse kinematic problem, I have enough information to define the transformation for L4, and I have J1, which becomes the new end effector for the next inverse kinematic problem, now between L3 and this other virtual link, right? Then we have enough information to decide the position and orientation of L3, and the solution of the intersection, which is J2, now becomes the end effector for the last computation, which is an inverse kinematic problem between L2 and L1, right, which is J3. So that is what we need to do. So what we can do is basically a recursive function that will always solve the problem for the last link. So we could send the ID, right? I mean the number of the last link. So maybe it can always solve for the last link, right? And if the last link is, yes, basically if let's imagine that it's a variable that at the beginning it says 4, right? It means that it will solve for this guy, right? So we can have something like if that ID, right, is larger than 2, right, which is basically the last computation that you need, right? The last time you are computing for the last link. If it's larger than 2 or something like that, we basically compute the last one and then recursively compute the next until we get to the end. Yeah, maybe something like that. So we need to have an animation. Animate on. And again, I will probably pause. Yeah, so something like this, right? So I am basically animating this, right? From time 0 to 100, and at time t, I will call this function that is not written yet, solve IK, and I will send the kinematic chain, right? Because that is basically the array of all the links, right? And I can send the last ID, yes, basically the ID of the last link, which in this case is kinematic chain.count, right? Which is basically 3. On 3D Studio Max, the arrays begin in 1. So this is 1, 2, 3, and yeah, just remember that. Yeah, C++, the arrays or vectors, something like that, they all start in 0. This language in particular, they start in 1. Okay, so now we need to construct that function, right? So we need to and again I will probably pause, right? Yeah, so we will basically get the kinematic chain, the end effector, right? The position of the end effector, which is already there, and the last link ID, right? I will call it like that, which the first time is kinematic chain dot count, right? The size of the axis, sorry, the array. So if I come back to the image, right? If every time we solve a kinematic problem, we're solving for two links, we already have that, and right, and it seems that we don't need to like code many things. The thing is, the trick here is that we will use virtual links, and those virtual links, the length of those virtual links, that's the tricky part, right? So let me explain what we need to do. Imagine that the position P is the end effector, right? So imagine that the distance between O and P, or basically like the entire distance from the origin and the end effector, is at the maximum distance from the kinematic change. So which one is the maximum distance of the kinematic change? Well, the sum of all lengths, right? So the sum of this distance, L1 plus L2 plus L3 plus L4, because these guys are, right, they're attached, mechanically attached, right? So they cannot go further than the sum of their lengths, right? The sum of their lengths, right? So that is basically the maximum distance. But P can be, right, either at the maximum distance, even more than that, right? But that is, for now, we will not care about that. Eventually, if you want to make this like very, very complete, you will need to, for example, like maybe like a if statement that if the end effector is farther than your maximum distance, you can basically, yeah, just like put everyone in a straight line and get your transformation part to like, yeah, basically to never have the problem of getting your links to be like disjointed, right? So they need to be obviously like stick together because they're supposedly mechanically stick together, right? But we're not worried about that. For now, let's just think of the end effector is either at the maximum distance or at any distance that is less than the maximum distance, right? So the thing here is, imagine what happens with the virtual link when the end effector is at the maximum distance, right? If everything is a straight line, right, it means that the length of this virtual link needs to be also its maximum length. So think about it. What would be the maximum length for V2 for this virtual link? Needs to be necessarily the sum of L1, L2, and L3, right? So basically, the maximum distance for each virtual link is its previous links, right? That is the maximum distance for the maximum length for this virtual link. The thing is, the virtual length needs to be variable, right? So how can we do that? Well, now imagine, right, that we need to define a minimum distance for this virtual link. So this virtual link is like a flexible link, right? They will like compress or stretch depending on something. I will explain what is that something, but imagine that these virtual links, the only thing is that they are basically like stretching, right? Imagine that they are basically stretching. So they can either stretch into the maximum length, which in the case of V2 will be the sum of L1, L2, and L3. And for now, imagine that we define the minimum distance from V2 to be L1, okay? And it kind of makes sense, right? It makes sense that if this guy is somehow representing this section here, right? This section of the kinematic chain, it kind of makes sense that its minimum length will be the first length and its maximum length will be the sum of all lengths. It makes sense. So now let's imagine the following case. Imagine that point P is not at 100% of its maximum distance, but is at half of the maximum distance, right? If this guy is at half of its maximum distance, it means that the length of B2 needs to be also at half of half of the difference between its minimum distance, sorry, its minimum length and its maximum length. Okay, so basically we need to compute those lengths. We need to first compute the maximum distance from the system, right? So we need to compute the sum of these guys, and we also need to compute the maximum length of B2, I mean, for each virtual link, right? So for the virtual link, we need to compute the maximum length and also the minimum length, and then the current length. And that will be depending on the actual position of P with respect to O, basically the current distance, right? Okay, so we need something like this. I will create this variable. For now, it will be 0. So system max distance it will be basically the sum of all these lengths, right? So because I will use plus equal, I need to declare the variable first. Otherwise, it will crash. So I declare the first I declare the variable at 0, and then I will basically loop, right, from 1 to last link ID, right? Because remember, this will be recursive, right? So every time we'll be like compute the last we will compute the inverse kinematic with the last so we will compute with the last link from the system, the second step from the recursion, this will be the last one, then this will be the last one, right? So we will not, the maximum distance every time will be changed, right? Because when we are in the second step, when we are basically considering J1 as the end effector, now the maximum distance of the system is not the entire system, but only from L1 to L3, right? So we need to, we need to go only up to last link ID, and we just accumulate from the kinematic chain L.height. Basically, we'll just accumulate all the distances, and then we have these the distance from the origin to end effector, which is basically the current distance, the real distance that is from the origin to the end effector, which is just the end effector minus the position of the first link. And this is not the virtual, right? This is the actual first link, because that is the real origin from the entire kinematic chain. And we take the length, right? Then we will need to get something like this, a distance ratio, right? So a distance ratio will be the current distance, the actual distance from the end effector, from the origin to the end effector, divided by the maximum distance possible, right? This distance ratio is the number that we will use to modify the distance from the virtual links, right? So again, the virtual links need to compress or stretch depending on how far is the end effector. If the end effector is at the maximum distance, if this number is exactly the same as this number, is the maximum distance, the other guy needs to also be at the maximum distance, right? But if the distance ratio is 50%, it means that the distance from the end effector to the origin is just half of the maximum distance from the system. We need to compress the virtual links, right? 50% of their entire mean minus max, right? So we need that. Okay, now we need to define the minimum distance for L1 and the maximum distance from L1, right? And remember, this will be recursive. So for now, I will call L1 to this guy, right? So in the first step, L1 will be a virtual link. On the second step, will still be a virtual link. On the last step, it will be a literally L1, okay? But so I will call L1. So we can say L1 mean, again, I will pause, right? So we have two variables, right? The minimum length from L1, which we already said that it makes sense that the minimum link for the minimum distance from the virtual link, the minimum length for the virtual link should be the one from the first link that it represents, right? V2, this virtual link here, is basically representing somehow L1, L2, and L3. So let's take this guy here as its minimum, right? So it will be this, right? Kinematic chain, sorry, not this one, the first one. And then, yeah, and then we just basically accumulate every length. Its maximum length, it needs to be the maximum of its own, this if it's from its own system, right? So the system from this guy is not the entire chain, but only L1, L2, and L3. So it always be last link minus 1, right? You agree? We only need, yeah, we are not obviously taking into account the last link, right? But only the ones that are basically from the last link to the back, right? Those are, yeah, that will be basically the maximum length. So now we can define the actual length, right? So now we have the minimum and maximum. Now we need to define what is the actual length that we will compute, right? And the actual length that we need to compute needs to be related with the distance ratio, right? So we can say something like length 1, it will be equal to its minimum distance, right, plus something, because it cannot be the actual length for the virtual link. It cannot be more than its maximum, but also not less than its minimum, right? So it needs to be its minimum plus something. So what is that something? That something needs to be related with the actual distance ratio. Remember, the distance ratio is the ratio between the actual distance from the end effector to the origin of the kinematic chain and the entire system maximum distance. So if the end effector is at 50% of the entire maximum distance, it means that from all the range that the virtual link has, right? So the virtual link has a range that goes from its minimum to its maximum, right? So from that range, it will need to be basically 50%, right? That means that we need to get the maximum length. Yeah, so the maximum minus the minimum, right, times the distance ratio, right? So basically this, right, the maximum minus the min is its range, and that range needs to be multiplied by this distance ratio, right? So that, in that sense, the virtual links will basically adapt to the actual distance from the end effector from the origin, right? And that will be the length 1. That will be the length of the first link that we will compute, from which we will compute the inverse kinematic chain. And we need to get the length 2, which is this guy right here, right? So this is L1, which is the virtual one, and this is L2, which in this case is the last one from the system. So it's the kinematic chain last link ID. Remember, this will be recursive, so every time we will just get the last one. Okay, then we need to define the intersection, right? So the intersection will be a variable from which I am calling this function right here, right? Remember our function that is computing the circle intersection, right? So we will call that function. We will send the origin of the kinematic chain, which is the origin of the position of the first link of the kinematic chain 1. Then we need to send length 1, which is the one in this case, or in this step, is the one from the virtual link. Length 2, which is the one from the last link, and the end effector position, and an up vector, right? So yeah, So I also need to compute the up vector, and this part is tricky because we were using 0, 0,0, 1. We were using this as up vector. You will see that this will not be as useful in this case. I'm already talk a little bit about that on the other video, on the video for the midterm extra. The thing is, if we are using always the same up vector, right, we will have a problem because our kinematic chain, so this is the up vector, right? So if we use this, because we are using cross products, right? Imagine that at some point I get P now is probably closer, so imagine that now P is way closer. So now L1 will not be like pointing on this direction, but now pointing on this direction, right? So if I take the cross product between, imagine that I'm taking the cross product between L1 and V, right? If I take that cross product, the resulting vector will be pointing out of my monitor. But if now L1 is pointing into the other side, right? So it's now pointing in this side, and I take the cross product in the same order, L1, V. Now the cross product resulting vector will be pointing into my monitor. So we will have those that like flipping problem. So I will leave it like this for now, and we will see how it behaves, and I will explain how to solve this problem, right? So again, we compute the intersection, and then we just apply the transformation, right? At the moment we are computing that kinematic chain, we have enough information to decide the position and rotation for only L4, right? Which is L2, right? And in this case, it's the last link, right? So we have that ID, right? So it will be kinematic chain like last link ID dot transform, and we are just calling, right? Look at transformation function. We send the intersection, the end effector position, and the up vector, right? We are also using the same up vector. Good. So now we need to make this recursive. So let me make a pause. Okay, so we can do this to make it recursive, right? So after we compute this, we can basically take one from the last link ID, right? And then we kind of just have an if else, right? If then else. So if the last link is basically larger than 1, it means that we are computing inverse kinematic problems using virtual links, right? So in that case, we just need to repeat it, right? If I was computing an inverse kinematic with a virtual link, I just need to compute it again, right? And then obviously the last link ID that I will send, it will have one less, right? So now the last link will be, right? So the first step was this one. So in the second step, now it will be L3. Because I'm still using a virtual link, right? Now it will be L2, and yeah. And yeah, so if the last link is more than 1, I basically do the recursion. If it's not, I can, okay, if it's not, it means that the last link that I've used is already the second link from the kinematic chain. It's already this one. It means that I'm only still need to define the transformation for L1, right? So I just define the transformation for L1, and that's it. And I think it's already done. I haven't run anything, so maybe I will have a lot of bugs or not. Maybe, I don't know. Well, I was kind of running when I was pausing, but I'm not sure if it will. Okay. Yes, I think it's working as I was expected, and this very weird behavior, I think it's because the up vector. Maybe I'm wrong. I'm human. Maybe I'm wrong, but I think I'm not wrong. Yes, I think it's because the up vector. So again, what is happening here is we are using the same up vector for everyone, and because look at this. It is actually happening when this guy is basically like going back, right? So if it's going back or forward, right? When it's going forward, look at the position of this remember, this intersection right here is basically representing the end effector for now this pair of links, right? So if it's on that side, basically this is the end effector and this is the origin for these two guys, right? But once this guy is coming and basically like flipping side, right? When it's flipping side, now it has a it's on the opposite side with respect to the up vector, right? Because the up vector is basically 0, 0, 1. So what we need to do here, instead of using the same up vector for everyone, we will need to compute a different up vector, maybe depending on the direction of OP, right? So something similar to computing this vector right here, right? This direction. So imagine that every time I compute my recursion, instead of using the actual Z value, I compute it with this as up vector, right? In that case, right, because I am kind of like updating the up vector every time, this will be basically it will be correct. Okay, so let me make a pause. Let me think about it. How can we do this? Yeah, okay. So basically we need to compute this guy here, right? So what we will do is we will get the vector from the end effector to the origin, and we will get a cross product between that guy and in this case, basically the one from the plane in which the plane that is like pointing out of my monitor, right? So if we get that, we will get basically this vector right here. It needs to be negative in this case. So so basically this, right, is end effector minus the origin of the kinematic chain, right? And I'm taking the cross product between that guy and in this case minus y. Now let's see what happens. And it seems that is correct. Yes, it is correct. So basically I'm getting this guy. And again, depending on the order, right? I made this guy negative because of the order. If I make this guy positive, now this guy is pointing down. It means that I could also just change the order of the cross product, right? Yeah, but like this. Yeah, exactly. Yeah, this is better because having a -1 there is kind of confusing. So that's it, I think. Yes. So let's see if it works. It should work for a larger kinematic chain, right? So I will do the same. I will create a tiny box, and this guy will be L01, and I will just, I don't know, a lot of things. Okay, now maybe it's too much. How many? Whatever. Yeah, like this. Okay, so if I go here, there's a trick in 3 Studio Max. I think I could do something like this. I could do something like kinematic chain is equal to I think it can be L00 and then this. I think this should work. Give me a second. For some reason these guys are not, it didn't take these guys. This should take this should basically make an array with all basically with all objects that have that their names start with L000. Yeah, for some reason it's not working. Sometimes it doesn't work depending on like the order in which you created those. So yeah, whatever. I just literally make it like explicit. Yeah, okay. I just make it explicit like this. It's just horrible, but whatever. Yeah, so I compile it again, and we have a beautiful kinematic chain. Yeah, that's it. And again, the beauty of this is that the position of the origin of the kinematic chain is is depending, well, I mean, in this case is the origin of the first link, right? So if the first link is attached to the body of your character, in this case to the body of the octopus, right? And you're doing that using matrices, right? You're just multiplying its transformation matrix times the one from its parent. You already know that, right? So if this guy has some animation, it doesn't matter, right? Because in the end, everything will be, everything will be computed in the correct way. So for example, I can maybe animate this guy from this position right here to I don't know, this position right here, and then to this position. Sorry, no, give me a second. I need to first eliminate all its animation, because otherwise that might have a problem. So I will get this guy here, and then get this guy, I don't know, here, and I will just and it's basically respecting that this guy is moving. Okay, so now let me show you something. Look at this. Because we have enough links, you will see that the shape of your kinematic chain will depend on how are you defining the virtual link behavior, right? So right now the virtual link behavior is that it is getting its range, right? Its maximum minus its minimum, and it's just multiplying that times the factor, right? But there's something very cool about this. If you modify the min length or modifying the function that, I mean, I'm not using any function, right? I'm just multiplying by a distance ratio, but you could maybe use another nonlinear function, whatever. But even if I just modify the minimum length that this guy has, you will see different behaviors, right? So for example, if I multiply this times something, I don't know, 1.3. So a little bit, so basically the minimum length of all virtual links will be not exactly this distance, but just a little bit more, right? A little bit more. So look at what happens, I don't know, 5. Yeah, 1.8, for example, it will basically start like leaning to the other side. Yeah, so in this case, yeah, I guess 1.3 is it's a good number, right? And yeah, and also look at how, depending on how how the end effector is basically traveling along this 3D world, the kinematic chain is also kind of adapting, right? And it's also turning, and this is because the way we computed the up vector, and because in the end the up vector is also kind of like adapting. Yeah, so this is it. This is how you can implement this. So yeah, it is very interesting. Okay, good. Thank you everybody. So this is the end of this video. I think there's nothing pending. So yeah, I will upload this video, and along with the one for the inverse kinematic answers for the extra midterm. Thank you so much. Bye.